The second approach is the indirect approach. It's actually a more powerful method. The indirect approach is view y as an implicit function of x Therefore, I am not solving for y in terms of x. I'm not going through this extra work here to apply the rules as we had in the past. I view y as an implicit function of x, which means I leave the equation alone, and then I apply the derivative operator. I'll just write d dx, write the symbols. I'm going to apply the derivative operator to the equation as it stands. I'm not going to alter the equation and start solving for y. Okay? So this is implicit differentiation. Okay? The indirect approach is nothing other than the topic of this section. Okay? So let's see how that looks. We had x squared plus y squared equals 1. Since the left-hand side is the same as the right-hand side, that means the slope of the left-hand side must be the same as the slope of the right-hand side. So therefore, I should be able to apply the derivative of both sides, meaning the derivative operator with respect to x or y, but I'm choosing x in this case. Apply it to both sides, and the result on each side should again be equal. Now we know the derivative of a constant is 0, and therefore the right-hand side is 0 in this case. And on the left, here's where I have to be a little careful. I'm taking the derivative of x squared with respect to x. This is no problem. This is all the rules we've had in the past. Really, the whole thing is the rules we've had in the past, but it gets a little subtle here for a moment, so just bear with. So the derivative with respect to x of x squared is, of course, 2x, as we expect. Because the variable here is the same as the variable, you might say, down here. But when the derivative distributes across here and then applies itself, right, using the sum rule, right? The derivative applies itself to both of these separately. So when it applies itself to the first one, it's your standard derivative. When it applies itself to the second one here, because it has a y in it, and we know that really this y is a function of x in some way that we have not expressed, given we didn't do this, because that's not the goal, right? You haven't done this in general for the problems you're going to do in the textbook. So this is not an option at the moment when you're looking from this viewpoint. So y here is a function of x somehow that we don't know. So I'm writing it like this just to remind us for a brief moment. And that function has been put inside the squaring function here. Right? So really this y squared is a function within a second function. So this is really a subtle chain rule going on when the derivative applies itself to the y squared expression. Okay? So therefore, when the derivative applies itself to the y squared expression, the power comes down first, because that's the outer function. So I get plus 2. Power comes down, the power lowers by 1, but I keep the inner function the same. So this is now y, I'm going to write to the first just to exaggerate this point. Right? 2y to the first. And I've got to multiply by the derivative of the inner function to complete the chain rule. Right? So 2y to the first times derivative of the inner function. The derivative of the inner function is dy dx. It's just the symbols. Right? There in symbols is the derivative of the inner function. All right, so let me rewrite this very quickly. 2x plus 2y. And you could use y prime here. I'm just using this notation. I do pretty consistently use the Leibniz notation for implicit differentiation problems, because even though your textbook doesn't do it much, you could take the derivative with respect to y right now, and I would want to know which variable that I'm taking the derivative with respect to, and so therefore the dd y, ddx, ddt, whatever variable it is, that notation is more helpful here than the tick mark, which does not really express what variable you're applying the derivative to. So you have 2x plus 2y dy dx equals 0, and now I just need to get, I've got to solve, right? Solve for this little derivative expression here. Solve for that symbol. Okay? So my derivative ends up being stuck inside an algebraic equation, and the goal is to isolate the dy dx like if it were some other variable. If this were the variable z and I said isolate z, then you should be able to subtract 2x and divide by 2y and find out what z is. The difference is it's a more complicated looking symbol now, either y prime or dy dx, but the goal is still just to isolate this piece and get everything else on the other side. So doing that, like I said, subtract 2x, divide by 2y, and dy dx by itself is now negative 2x over 2y, which of course is negative x on y. All right. So there's our derivative for all time for this relation, the unit circle positioned at the origin. Now, if you look, you'll notice that this is exactly what we found over here in a wildly more efficient way. Right? So it's not obvious at first, but if you look at it, okay, the first rule here for the derivative for the upper half of the circle was negative x on root 1 minus x squared. But root 1 minus x squared, right, that little expression there, was nothing other than y itself. The y for the upper half of the circle is root 1 minus x squared. So this first derivative we took here for the upper half of the circle really is negative x on y, just like we found here. So to the lower half of the circle, if you look at the rule for y, it's negative of the previous expression. So therefore this down here, the root of 1 minus x squared, when I'm talking about the lower half of the circle, this is negative y. So therefore I will get x on negative y, which is of course the same thing. So really these two expressions were the same as long as I take into account that y had a different expression in terms of x for each part of the circle. But over here we found it all simultaneously, didn't break into any parts whatsoever. But there is one small thing. In these problems, because the relation is not a function, I will have to know which y coordinate, because there's more than one, right? It doesn't pass the vertical line test. So for a particular x coordinate, there could be more than one y coordinate, as we saw in the circle. And I would need to know what the appropriate y coordinate is that I'm dealing with, but usually the textbook just tells you which one it is anyway.